Okay, hello again, everyone. So yeah, I guess everybody are here already. So does anybody possibly have any question about this? You know, the slides I show in the lecture. Well, I mean, if it does not come to your mind now, you can always ask me Slack, and we can already start on that.
Okay, so we can start.
Yeah, go ahead. Thanks.
Okay, hello everybody. I hope you're all doing well. We are in week 10, and the topic is dimensionality reduction. Okay, so what is on? I hope it will work. Yes, it should work. Okay. So what is the dimensionality reduction? Basically, this is the transformation of data from a high dimensional space to a lower one. And this is useful for classification. We will see this, and this is also useful for data visualization, because if you have, for instance, 5 features at the beginning and you can reduce it to 2, then you can visualize it in 2D, for instance. And we will also see this. This is the first. If we go through the table of contents, this will be the first topic. We will see how to go from 5 dimensions or more, or from a high dimensional space to a lower 1 to 2, in order to be able to visualize it, the data. And then we will show an example of text classification with versus without PCA. PCA being principal component analysis. This is one of the well-known dimension reduction techniques. And finally, we will do a bit of TSNE, which is another one, which is non-linear. And again, we will use it to visualize text. So SMS from today and the complaints data that we had, I guess 2 or 3 weeks ago in text analytics 2. Okay, so basically the idea, we have a high dimensional space and we want a lower one. And of course, it is obvious that we want to retain a maximum of properties of the original data by reducing. So we don't want to lose a lot of properties or yes, of the data. Okay. So let's start with some packages and with the basic example. So the idea of PCA is to project the data, all points in a lower dimensional space, but in the direction that retains maximum variance. In this example, we want to so we have two dimensions, x and y, and we want to project the data in only one dimension. And if you want to do this, it is better to do this to project each point on this line, because V2 is greater than V1. So we will keep a maximum variance in this case. So if we do the projection of all points on this line, on a line that would go through this, we will keep a maximum of information, because close points will remain close, and points that are more further away from each other, they will then also be further away. For example, this one will be projected around here. This one, which is far from this one, will be projected right here, and this distance will remain approximately the same. So this is an example from 2 to 1 dimension, but we can go from, and we will see this also, from 1,000 to 100 dimensions, for instance. So it is not limited. Okay. And to illustrate this, I have some data on breast cancer. So we have basically 5 features: the radius, the texture, the perimeters, the area, the smoothness, all numbers. And then we have a diagnosis, so 1 or 0. And we want to use, of course, this is a classification problem. We want to use those 5 features to predict the diagnosis. Okay, what is useful to do in the case of linear dimensionality reduction techniques is to plot the correlation between the features, and we can, for instance, see in this case that we have the radius that is almost perfectly correlated with those two, the perimeters and the area. And this is then useful to know that, okay, we can maybe combine them and reduce the dimensionality. And we will see that we will be able to do this quite well in this case, because some of the features are highly correlated. So 1 and almost 1 is really high. So we won't lost a lot of information, a lot of variance in this case, and we will see this. So correlation coefficients are useful to know if it's possible and if it makes sense to apply a dimensionality reduction technique. Okay, so we select only the features. So we drop the diagnosis. So we have our features. We can try with and without standardization. Here I don't use it, but you can try to use it and see what's the difference in the results. And then we apply PCA. So we have from Escalern decomposition PCA. We create an instance of the class with 2 components. So we will reduce from 5 to 2 components. And then we make a data frame from the components, and we plot the explained variance ratio. This means how many % each component takes into account from the variance, from the total variance of the data. So if you have, and then I do the sum of it, and the more the sum is close to 1, the less the variance is lost. So the better it is. And we will see in this case, if I run this, that the variance ratio, the total variance ratio of basically the first component is almost 100%, and both components are like almost 100% of the variance of the initial variance. And here are our components, so 1 and 2. And then it is useful because we can plot them in 2D. I first concat, and then I plot this with the diagnosis, and we can see in this case that it works because we kept a lot of variance, and then it is useful to, so it is first useful to visualize it, but also then to apply any classification algorithm. So we can see in this case, we can separate data quite easily, and we will have a high precision. Okay. So that's it. We create an instance of PCA, and we fit transform the data, and then that's it. Okay, any question on that? Okay. Yes, I forgot to say that we will have the quiz afterwards at 4:30. So the lab will be a bit shorter today. Okay. If there is no question, we can do the exercise, the participation exercise of the day. So you will have 10 minutes in groups. I will break out the room, the session. You, as always, you can send you send it to me on Slack, and you can also because Professor Vlachos also told this in the class, so you can not only send it to me like personally, but if you mention the members of the group, then it will also be fine. And the deadline is tomorrow at 6 p.m. Also, Professor Vlachos also told this in the mail. Okay, and the idea, I first read someone in the chat. We should stay in this Zoom for quiz. Yes, yes. I will stop with the lab session like 10 minutes before, so at 4:20, and then you will have 10 minutes to get ready, and so you have to stay in this Zoom session. Okay, and the idea is to illustrate PCA with 3D data. Oh, there is something else in the chat. I don't. This quiz will be also be open book, right? I guess, but Ahmad will tell you the instructions at the beginning of the quiz, so no worry. That's why we have 10 minutes. Okay, the idea for the exercise, the idea is to show PCA in 3D and to reduce it in reduce it in 2D. So I have a function here. So it generates a plane with some noise. So endpoints belonging to a plane with a bit of noise, E. And for instance, if I want to have 500 points with a noise of 50, it generates the points, and then I can plot them in 3D to show you that we have a plane, and we want to. So it also generates 2 points. I forgot to say 2 points that are a bit further away from the plane. You will see why while doing the exercise. So those 2 points are a bit, they belong to the plane, but they are a bit like further away. And we want to apply PCA. That's your job now, to apply PCA to this data and to show which cut it makes. So basically, the idea of PCA from 3D to 2D is to take a picture from this data that keeps a maximum variance. So you will see in the results, if you take the picture from here, you don't keep a lot of variance, but if you take it from here, you will see that you keep a lot of variance. So okay. So the idea is to implement PCA with 2 components. So we go from 3 to 2 to tell me what is the explained variance ratio, and then to plot the 2 components. Okay, let's break out. So you have until 41. There is something. So basically the outcome is the same points, but in 2D, right? The outcome should be the results of the PCA. So you have to plot the 2 components. So as it's the same as just above. We had 5 components. So we went from 5 to 2 using this PCA.fit transform of the data, and then we plot it in 2D. Then we see that there is a we saw that there is a clear separation, and the idea here is to do the same with this data and to see how the PCA do this and what's the result. So, and then to plot it in 2D again, so to plot the two components. Okay, let's break out. So you have until yes, 42. Okay, 10 sessions. Maybe 9. 9 is fine. Okay, so until 41. Until 341.
Il y a quelque chose, Luc?
Non, je voulais voir, t'es tout seul, tu veux que je change de groupe ou bien?
Non, 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 ça va bien. Je suis en train de tout à fait à côté. Ça va très bien.
Ok, parfait. Parce que j'ai vu que t'étais tout seul. Alors à toutes.
À toutes.
Okay. Did you succeed in the exercise? Was it okay? I guess it is not so complicated. Basically, you have to copy and paste the code above. So there is from Brian something in the chat. Is PCA just a bird view of the 3D graph. Can you recall what is its use? Okay. Yes, in this case, because we are projecting in 2D, the idea is to find the best place to take a picture, because the picture will be then in 2D. So if you do, I will show you in MDS, sorry, the results, a similar result to, because I will apply to the same plane. So this multi-dimensional scaling. But basically, it's as if you would take a picture of the plane from the best location that keeps a maximum variance. And there was a second part. Its use? There are mainly two uses to it. Data visualization, as we showed here, because you can, if it's if it's 5-dimensional, you cannot visualize it well. But if you reduce to 2, then you can visualize it. And also, it can improve accuracy and time for a classification algorithm or regression algorithm. So you can improve your results. We will see this in the second part, basically. In this part, we will compare with and without PCA text classification. Okay, so if there is no further question, I also provide an example of MDS. So that's basically MDS is another way to reduce dimensionality, but instead of focusing on the points, you focus on the distances, so the Euclidean distance in this case, between the points. So I have here a plane without noise, so the noise is 0. And basically, I guess this is the same plane, but without noise, because the noise, I will add the noise to the distances. So I standardize it because we calculate distances. So it's always great when we have to do with distances to standardize. So this yields something like this. Then I compute the distance using from a scalar and the Euclidean distances. The Euclidean distances is the square root of the difference of the square. So this, for instance, I can run this, but for instance, this 2.94 is the Euclidean distance between the first and the second point. So between this point and this point, and basically what it does the square root of the sum of the differences square. So this minus this square plus this minus this square plus this minus this square, and the whole, you take the square root of the whole. Okay, so you obtain a table basically with, of course, the distance of the first point to the first point, or the second point to the second point is always 0, and then you have first second, and it's the same at second first, then, and so on and so forth. So the distances, and I add a bit of noise to those distances, like this, with random noise of size and samples. 500, we had 500. So for instance, 294 is now 3.4, then a bit of noise, yes. So each value is has changed a bit. And I ran this multi-dimensional scaling with 2 components again, and some other parameters. And I fit transform the similarities. So that's the main difference between PCA and MDS. MDS focuses on the distances, and PCA on the points. And if I run this, it takes a bit of time. And I can also run this here. You have a question? You have a question? No? Okay. And so we have the components, the two components, and the projection, and we can see that basically you should have obtained also something similar to this with the PCA example. So we can see that it's as if we have taken a picture of the plane from above or below, but with maximum variance. So those 2 points, if you remember those 2 points, if we take a picture from here, this should do the job basically. So the idea, you take a picture that maximizes the variance, that keeps a maximum amount of information, because we go from 3 to 2 dimension. So it should be clear. Is it clear? Any question on that? Okay. There is something. All good. Okay. So we can have a more realistic real life example with SMS classification, and we will compare, we will use logistic regression and KNN and compare the case with and without PCA, and also the runtime. So the data is about, that's basically easy. We have SMS with the message, the text, and then whether it's ham or spam. So ham is basically great. Spam is, you know what spam is. And then, of course, we want to predict the label. So if it's ham or spam, based on the text message in those columns, we will drop them. And yeah, we'll drop them because they are almost all null. So we drop using the drop methods. We drop the column, then we rename the V1 in label and V2 in message. And this yields something like this. So we have the message and the label we want to predict. Okay, and we have 5,500 something entries. Okay. And what we can do is first a bit of EDA to have an idea of the data. So we have 2 classes. It's an imbalanced data set because we have 4,600. That's also quite logic, because most of the SMS, of course, unfortunately, most of the SMS you got are ham and not spam. And then you have an example. And we can also, we have also an histogram of this to show this, and the base rates, which is the probability of the most probable class, is 86.6 around. Okay, we select the variables. So Rx is the message, Ry is the label, and I can stop there and ask if there is any question on this so far. Okay, if there is no question, as always, we perform a train test split. So from sklearn, this function, you know this. And then we use a test size of 20%. and a random state of 72. And we get a train test split here. So this is, for instance, our training data X-train. Okay. Then the next step, of course, because we have text data, is to clean and vectorize it. And in this case, I show you another way, another package to do this. You can try it in your project if you want. Instead of Spacey, we can use NLTK, which is another package to do text cleaning and tokenizing. And you also have the stop words. You can also do stemming. We'll do this in the function here, and also this package to remove the digits, to remove the punctuation, and so on and so forth. So we define the stop words in the English because we have English messages. Then we import the tokenizer and the porter stemmer to do stemming of the words. Stemming is we cut the ending to have the same word for a different form of the words, like weight, weights, weighting, weighted, and so on and so forth. We remove the digits. We lowercase using lower. We remove the punctuation. We remove the stop words. We tokenize using the tokenizer we imported from NLTK. We do a stemming using the porter stemmer, and then we return it. And I show what's the result on X-train when I apply the data cleaner in the function. Okay, if I run this, we get, for instance, for the first one, which was mom wants to know where you blah blah blah. We get something like mom wants to know, because it removed the stop words. For instance, the to, the where, you, and so on and so forth. So those stop words. Okay, so that's our cleaning and tokenizing function. And we use TF-IDF in this case. So we use our tokenizing function, or cleaning and tokenizing function in the vectorizer directly as tokenizer with only 1 grams, and those other parameters which are the minimum occurrence of a token to be taken into account, and the maximum proportion of documents in which a token becomes in order to be taken. If a token is in 95% of the documents, it won't be taken into account, for instance. Or in 95% of the messages in this case. And then we fit and transform using our TF-IDF or instance of this class that we just declared, X-train, of course, and X-test. And then I also print the shape because we are interested to reduce the dimension. So it's useful to know the shape. Okay, I run this. And we can see that we have our 5,557 instances, and the dimension of this matrix is 1,957. And now we can use PCA. So we want to lower the dimensionality of almost 2,200, for instance. So we declare, we create an instance of the class, and then we transform, fit transform, and we can also print the shape, but we already know that it's 100, and the number of component also, and also the explained variance ratio. Okay, if I run this, we can see that we transformed our messages to only 100 dimension instead of 2000 around. And we have an explained variance ratio of 33%, which is low, I would say, but it's something. And what is useful to know is that you can also, in this case, specify a percentage, for instance, 90%. And if I run this, it means that it will compute the component such that it keeps 90% of the variance. So in this case, if you would have 943 components, then it will keep 90% of the variance minimum. So either you specify the number of components or the percentage variance, total variance that you want to keep. Okay, and then we can compare. So we will run logistic regression 4 times, once with PCA and standardization, then then only with standardization, then only with PCA, and then with both of them. And then we will compare the runtime and the accuracy on training and test sets. So this is the code. Basically, this is always the same. The only thing that changes is the pipeline. So in this case, we only have logistic regression in the pipeline. I start ends with the time that we saw last week, and I fit in the middle, and then I print the time, I print the train accuracy and the test accuracy. And if I run this, I just run everything now because it will take a bit of time to run. Okay. Okay, so without PCA and standardization, the base rate was like 86 or 87, and we can see that we are above it. So, and the time is quite, it's quite quick, and we have the really high accuracy, and we did better than the base rate, so we are fine. Only with logistic regression. Then, if we use standardization, we can see that the accuracy is even better, but of course the time is a bit lower because you have this second element in the pipeline in which you have to scale the data, so to standardize the data. But the accuracy is like 1 or 2 percentage points higher in this case. Then only with PCA, so we add the PCA elements in here, we can see that time is even higher and the accuracy is lower. So in this case, PCA is not useful. We may change the number of component. Of course, here we had 100. We may test with 1,000. We may test with 10, with 500, or with a specified percentage, as I showed you earlier. Okay. So with PCA, in this case, it does not increase the accuracy. And if I do both PCA and standardization, it increases the accuracy compared to the single case, compared to the case only PCA, but it's not better than only standardization. So in this case, with logistic regression, we can see that standardization increases the performance, but PCA does not. Okay. Any question on this part? Okay, if there is no question, let's do the same basically with another algorithm. So we use k nearest neighbor, and we change the component to only 10. So basically, we go from around 2000 to 10 components, to 10 dimensions. So that's basically really low, and we use k nearest neighbor classifier with 15, sorry, with 15 as parameter. So in the case of only so without standardization and without PCA, we can see that okay, time is like 1 second 27, and the accuracy is quite low, just above the base rates. So it's not so great. And if we use standardization, it is not completed to run now, but we can see that time is almost the same. So now it's done, and accuracy is even lower. So standardization is not helpful in this case. And here it's becoming interesting, because we can see that with PCA and only 10 components, we improve the accuracy by almost 10 percentage points, with a time that is divided also almost by more than 2. So that's great. Accuracy is 96, and accuracy is higher and time is lower. So with a big data set, this may yield a big difference in terms of first accuracy, of course, but also time. And then last, we have the same with PCA, with both PCA and standardization, and we can see that the time is, of course, a bit higher than this, because we have this additional step, but the accuracy is not higher. So it's higher on the training set, but not on the testing data. So in this case, we can see that PCA increases the accuracy, but standardization does not. And in addition, the time to run is lower with PCA, because we only have 10 components instead of 2000, around 2000. So the time to compute the neighbors and so on and so forth is lower, of course. And it compensates more than the time to transform, because you also have to transform your data into only 10 components here. So it's, in this case, PCA helps. And finally, the conclusion to be drawn from this is that PCA and standardization, and also other dimension reduction techniques, are useful tools that could help increase the accuracy and or lower execution time. So you may want to test it in your project, for instance. Okay, any question on this second part, where we compared PCA with PCA and versus without PCA? Okay, no question. Is it clear? Is it too fast? Is it? Or you're all working on the quiz? I don't know, or sleeping? Okay, all is clear. Okay, and then at the end, I have an example of this TSNE. So you have documentation, you can find documentation Basically, it's the same manifold is the same as for the MDS, sorry. And then you can read this documentation if you want information. And basically, TSNE is also a dimension reduction technique, like PCA or MDS, but it's non-linear in this case. So, and it's also based on distances. If I'm right. And I provide here two examples. The first one, we use the training data vectorized of the SMS. So this one basically, this is the result of TF-IDF. So you have those almost all 0, and sometimes you have a value because word number 4 is in document number 1. That's the TF-IDF matrix. Also, there is one here, for instance, and also one here. And you have like a dimensionality as before because it's the same example of around 2000. And we want to reduce it to 2 in this case to be able to visualize it in 2D. So we use this TSNE visualizer. The documentation is the first link if it's not the second one. Yes. And the documentation is here. By default, you have two. So it's not by default. You always have 2 because it's in 2 dimensions. So you always have two dimensions for the reduction. So this means that we go from this 2000 dimensions to only 2 dimensions. And then we plot it because this is a visualizer, so in 2D. And basically I can run this. So as always, we create an instance of the class, we specify the color we want, and then we fit it. So basically it takes this matrix and gives you something in 2D that is optimized to like in PCA, but it's based on distances in this case, to keep the most information, the most variance, the most to keep the most information basically. And if I do this, we saw that in 2 dimension we have our spam region, I would say, and or ham region with some spams that are a bit here, but we can see a separation in, and it's a good result because so we went from 2000 to only 2 dimensions. So that's great, even if there are a lot of zeros and it's an easy case in this case, of course, but this is impressive to go from 2000 to only 2 dimensions. And I can do the same as last example. If you remember the complaints, those ones, so we had complaints with a text and then a product to which it was to which it belonged. So for instance, credit reporting. So this was an example 2 or 3 weeks ago. And in this case, I used the same code as in the previous lab session. And we also have a TF-IDF. And the TF-IDF gives you something that has a dimensionality of 8100. And if I do the same with this TSNE visualizer, then it yields something. It gives me something like this, where we see a bit of the cluster, but since we have 12 classes, this is not so. So yes, we see a bit, but we don't see. There is a lot of stuff we cannot so see with this method, because maybe we have too much classes. Maybe we from 8,000 to only 2 dimensions. This is too much. It should be too much. So in this case, it doesn't work so well. But we can see a bit some clusters in this case. Okay. So this, I think we are done with this lab. If there is no question, is there any question on this lab session, on anything that is unclear, anything that should be re-explained? Or you are all preparing for the quiz and don't care about this lab? Okay, if there is no further question, no more question, then I can say that it's done, and that Ahmad will give you. So we take now like 5 minutes break, and at 4:20. So you have to make you ready, of course, to make your video on. You know the instructions, but Ahmad will say them again. And at 4:20, he will start with the instruction, and then at 4:30 we will open the quiz, so you can then start in 16 minutes. Okay. So see you in 5 minutes, and thanks for attending. And if you have any question, then you can ask. You have 5 minutes.